So we need to talk about just a few more things before we get into chapter 12 today. And so we've talked about and gone over epoxides, and we've talked about their chemistry. And so if we have just an R group out here, and we talked about the fact that under acidic conditions, nucleophiles attack an epoxide at the most substituted carbon because that's the weakest bond, right? Because that oxygen is protonated. But under basic conditions, we attack the least substituted carbon because of steric hindrance. There's no steric hindrance or less steric hindrance there, and the reaction can proceed. Now, in both cases, those epoxides are reacting in such a way that we open that ring, right, and that relieves ring strain. And so we know that epoxides are a lot more reactive towards nucleophiles than a typical ether. So an epoxide will react very easily with a negatively charged nucleophile, whereas diethyl ether doesn't. You can have very strong nucleophiles in diethyl ether, and no reaction will occur. Whereas if you put an epoxide in there, the reaction will occur quite readily. And it's all because of ring strain. One of the things that we did not talk about, however, is how we make epoxides. Okay, so if we think about it retrosynthetically, it turns out that an epoxide is the reaction of an alkene plus an oxygen atom. Okay? Think about it. All we're adding is an oxygen atom across the carbon-carbon double bond. How many of you think we can go buy a bottle of just oxygen atoms? You can't, right? They don't exist. We have to have a reagent that allows us to do this type of chemistry. Does anybody know what those reagents are? What reagent do we need to take an alkene to an epoxide? We need a peroxy acid. That's right. What we need is something that looks like this. Doesn't really matter what R is, but it is a peroxy acid. It looks like a carboxylic acid with an extra oxygen. And it turns out that it's this oxygen right here that can behave like an oxygen atom. And it can add across the carbon-carbon double bond in a way in which we get epoxides. There are two of my favorite peroxy acids that you need to know by heart. The first one goes by the name MCPBA. It stands for metachloro peroxybenzoic acid. Don't worry about the meta yet. We haven't gotten into aromatic nomenclature. But it looks like this. It's a nice white crystalline solid. You can obtain it fairly pure. You simply weigh it out, you put it in with the alkene, the reaction occurs, and you get an epoxide. The other one is peroxyacetic acid, where this is a methyl group. Both of these will work. But what you need to know is that any peroxy acid will react with an alkene to generate an epoxide. Okay? The mechanism, there's a lot of arrows that go back and forth. I don't really care that you know too much about the mechanism of how the epoxide is formed. The only thing that I want you to know is that it's a concerted reaction. The two bonds between the oxygen and the two carbons are being formed at exactly the same time, more or less. And that has a stereochemical consequence. For example, if we start off with a trans alkene and we react this with MCPBA, we will get a trans epoxide. The stereochemistry of these two R groups is retained. Here it is trans there as well, and it's 100%. It's very stereospecific. And so if we start off with a cis alkene, what do we end up with? We end up with a cis epoxide. And I'm just drawing the two R groups coming out of the plane of the board. Okay? could have just as equally drawn them both going back. It doesn't matter. Okay? So this is one of the easiest reactions in the world to do, is epoxidation with a peroxy acid. You literally mix the two things together in some solvent like dichloromethane. The reaction's over in about an hour. You work it up and you've got your epoxide. And if you want a trans epoxide, you need to start with a transalkene. If you want a cis epoxide, you need to start with a cis alkene. Okay? Any questions about any of that? It's one of the last things that I wanted to talk about. So we know how we can form epoxides. Okay? Using those types of reagents. Today we're going to get to talking about a little bit about oxidation and reduction in organic chemistry. This is not a brand new topic. We've talked about it before a little bit several chapters ago. We're going to talk about how we can make alcohols by reduction. So far we've made alcohols how? Addition of what? Water. We've added water across carbon-carbon double bonds, okay, for example. And we could add that with just catalytic acid and water. We did the oxymercuration demercuration sequence, right? If we don't want carbocation rearrangements, we talked about anti-Markovnikov alcohols by using the hydroboration oxidation sequence. But in all cases, we're adding water across a carbon-carbon double bond. There are ways in which we can get alcohols by reducing carbonyl groups, and we're going to talk about that today. We can take a carbon double bond oxygen and we can reduce it by adding hydrogens across that double bond to get an alcohol. So you're going to learn many, many ways in this class how to make alcohols. And so we'll talk about that, and then we're also going to talk about how we can oxidize alcohols and make other functional groups. So far we've learned that we can take alcohols and we can eliminate water to make alkenes. We've learned that we can take alcohols, convert them into alkoxides, and do the Williamson ether synthesis and make ethers. We've learned that we can take alcohols, react them with hydrogen halides or PBr3 or SOCl2 and convert them into alkyl halides. Alcohols are extremely useful functional groups. And so we're going to also learn today that we can oxidize those alcohols and actually get carbonyl-containing compounds. So exactly the reverse of the reduction, okay? So alcohols are a very, very important functional group, and we can convert them into a lot of different things. And so hopefully you'll leave with a little bit of an appreciation for that. This is an example of some reactions that we've already talked about in 255. And this is my kind of roadmap example. You all know that I like roadmaps. If you haven't been involved in developing roadmaps, you really need to get into that habit now. Because from this point forward, a lot of what we're going to go through is reaction after reaction after reaction. You already have, and this is no joke, you already have about 85 to 90% of everything that I know has been presented to you in terms of mechanisms, SN1, E1, SN2, you know all that stuff. You know about free radical reaction mechanisms. We're just going to start, in this class, we start placing it in different contexts to lead to different reactions, okay? So you really need to be able to look at a functional group and know what you can transform that into. And so far, this is kind of an example of what we've learned that we can do to an alkene, as an example. You should also have one for alcohols. Then you'll have one for ketones. Then you'll have one for amines as we get to those parts in the chapter, okay, or different chapters. But just think about all the things that we can do with an alkene. We can add water across it in an anti-Markovnikov fashion. We can add water across it in a Markovnikov fashion. We can add two OHs across the double bond, make a syn diol. We can add, we can make bromides. We can make, what have I got here? We can make alkanes. We can make halohydrins, so on and so forth, right? We've learned that we can do an awful lot of things with these things, and the only way that I know how, personally, to keep good track of this is to build these roadmaps. Some students in the past have called them spider webs, because they start to look like they web out, but these types of things are very, very important for you to be able to grasp. So you need to know on site what you can do with a functional group, and this is a great way to organize that. Here's some example problems that I want you all to work on your own. Not today, but I'm going to post the answers to these next week. So I'm going to give you some time to work on them. None of these reactions have we ever talked about explicitly. I have never taught you how to take one alkene and convert it into a different alkene. Yet you have all the tools in your toolbox to do that. I have never taught you how to take an alkene and make a this dihalide where you have a bromine and iodide both facing the same direction. I've never taught you that explicitly, but you have all the chemistry that you need to do that. I've never taught you how to take one alcohol and convert it into another, but again, you have all the chemistry that you need to do this. Okay? This one, yeah, I've probably taught you how to do this one. Okay, but nonetheless, I want you to focus on it. You will struggle through some of these problems. I want you to struggle through these problems. These are a little higher level than what we've been dealing with before, okay? And then I'll post the answers next week. You'll self-grade it yourself, okay? I'll put up some explanations for it. But multiple steps are required. You can't do this, at least with the chemistry that you know, you can't do any of these things in simply one step, okay? So these are on the slides on Canvas, so you can just print this off and work on them a little bit, okay? So we know what the carbonyl group is, right? We know that the carbonyl is a carbon-oxygen double bond. We know that the carbon is sp2 hybridized. We know the oxygen is sp2 hybridized. We know that one of those bonds is a strong sigma bond and the other one is a weaker pi bond, right? We know that. We know that that bond is polar, and the dipole lies towards which atom? What's that way? The oxygen, right? It is a dipolar molecule, right? Where the carbon is partially positive, the oxygen is partially negative because of the electronegativity differences, right? We know that, as an example, the carbonyl belongs to a variety of different functional groups: aldehydes, ketones, carboxylic acids, esters, just as an example. There are others that we learned about as well, right? And if you think about this, if I take an alcohol, so that's a terrible green now that it's projecting. If you take that alcohol, if you imagine just removing these two hydrogen atoms and replacing them with a pi bond, that's an oxidation reaction because we're removing hydrogen from a molecule, right? You can get to, in this case, a ketone. Likewise, we can imagine adding hydrogen across this carbon-oxygen double bond and getting an alcohol. So alcohols can be oxidized to ketones, and ketones can be reduced to alcohols. The same thing goes for aldehydes and even carboxylic acids and esters, and we'll talk about those as well. But in one direction, we have oxidation, and in one direction, we have reduction shown there, okay? So you need to remember that oxidation in an organic molecule is the removal of hydrogen or the increase in the number of bonds that we have to electronegative atoms. And reduction is the addition of hydrogen or the reduction of the number of carbon electronegative atom bonds that we have. Okay? So, just a little brief introduction there. We know that we've already talked a little bit about this, right? We got the planarity. We know that this is a trigonal planar functional group, right? The bond angles are about 120 degrees. The pi bond is above and below the plane of the board, if you think about this being the plane of the board, right? And the pi bond is the weakest bond. So if we're talking about adding things across that double bond, we're talking about doing chemistry on that pi bond. It's the weak bond. The sigma bond remains largely unchanged. Okay? We also know that we can draw a resonance structure for carbonyl-containing compounds, right? We can simply take the pi bond and break it and move those electrons onto oxygen, and we would have this resonance structure. It is a minor contributor to the overall resonance hybrid, and why is that? We have separation of charges. Very good. What else? What else about that molecule tells us that it has to be a minor contributor? What does carbon not have that it would like to have? Or a octet of electrons, right? So it doesn't have an octet, and we have charge separation. However, just because it's a minor contributor doesn't mean that it doesn't tell us something about the functional group or its chemistry, right? Even though it's a minor contributor, if you take this and add it to this, what you get is something that kind of looks like this, where you have a partial positive charge on the carbon and a partial negative charge on the oxygen. And so if we're going to add nucleophiles to a carbonyl functional group, what atom would it attack? It would attack the carbon. And why would it attack the carbon? Because it's partially positive. Nucleophiles have lone pairs of electrons, and quite frequently they have negative charges, right? They are not going to want to go to an area where there are already a lot of electrons. And that area would be the oxygen atom, right? Because it's got lone pairs around it and even has a partial negative charge. So we're going to find that the nucleophiles are going to want to attack the carbon of the carbonyl and break that weak pi bond. That's the chemistry that's going to be dominant in this chapter. Nucleophiles almost always attack the carbon of the carbonyl first, okay? And so that's where the chemistry of a carbon-oxygen double bond differs from the chemistry of a carbon-carbon double bond. How many times did we have a nucleophile attacking a carbon of an alkene? You can't think of one because it didn't happen. We always had the alkene attacking some electrophile, right? And it's because carbon with a negative charge is a poor leaving group. So if you think about a nucleophile coming in and attacking the carbon-carbon double bond, the resulting carbanion is just too unstable, okay? Now there are examples where nucleophiles attack carbon-carbon double bonds, but they're special carbon-carbon double bonds, and we'll learn about them later, okay? But for right now, this is why we see the chemistry difference between a carbonyl and an alkene. Even though they both contain a sigma bond and a pi bond, and they're both sp2 hybridized, their chemistry is actually quite different, okay? Now, in a generic oxidation and reduction reaction, you'll find people using either O in brackets or H in brackets. That O in bracket generically means oxidation. You don't know what the reagent is, you just know that you need to do an oxidation on this alcohol to get to this carboxylic acid. That's a functional group transformation. Now there are specific reagents that do that for us, and you need to learn those, and we will, but you need to know that this is just a generic oxidation. The reverse of going from a carboxylic acid to an alcohol is a reduction, and we can just put that in brackets as H, just telling us that it's undergoing a reduction reaction, okay? Do these carbon atoms have the same oxidation state? They do not, okay? And you need to understand a little bit about oxidation state in organic chemistry. And we talked a little bit about this, I think, in 255. It is very similar to calculating formal charge, except it has one exception. In formal charge, remember when we calculated the formal charge, we assumed what about the electrons in a bond? They were shared and shared equally, right? We made that formalism, right? That if there are two electrons in a bond between two atoms, they're shared equally, right? That is not true in oxidation state. In oxidation state, we do not assume the equal sharing of electrons. We make the assumption that the most electronegative atom will get the electrons assigned to it in the bond, okay? And so to actually calculate the oxidation state, it's the valence electrons minus the assigned electrons. Very similar to how we did formal charge. Remember, we came in with the number of valence electrons from the periodic table, and we subtracted the number formally owned. The difference here is you come in with the valence electrons from the periodic table, and you subtract the assigned electrons. So, if we look at this molecule, right, this is ethanol, and we want to calculate the oxidation state of this carbon, What we recognize is that there are two bonds to hydrogen, there's one bond to carbon, and there's a bond to oxygen. So if I'm looking at this yellow bond, the electrons in this bond actually belong to oxygen. I assign those two electrons to oxygen and none to carbon in that bond. What about these other bonds, these hydrogen bonds? Why would I assign them to carbon and not to hydrogen? Carbon is slightly more electronegative than hydrogen. And so that's right. So the electrons will belong to carbon. Now, we have a carbon-carbon bond. What do I do there? I have to split them. The electronegativity is the same for all practical purposes. So one electron goes to this carbon, one goes to the carbon that we're trying to calculate the oxidation state for. So we know that carbon comes in with 4 valence electrons, and it now has 2, 4, 5 electrons assigned to it. This carbon atom is in the -1 oxidation state. What is its formal charge, however? 0. So even though carbon can have 0 formal charge for a variety of different oxidation states, right, it still tells us something different. Okay, so this is in the -1 oxidation state. And so the more negative, the more reduced the carbon is. The more positive, the more oxidized it is. Okay? So you need to keep that in mind. So let's look at a couple of examples. Do a quick little concepts test here. Take a couple minutes. Work with your partner. What is the oxidation state of each carbon in the following 2 molecules? So methanol, what's the oxidation state of this carbon? And formic acid, what is the oxidation state of that carbon? All right, so what's the oxidation state of the carbon in methanol? It is -2. What is the oxidation state of carbon in formic acid? It is +2. What is the oxidation state of carbon in carbon dioxide? Four plus, right? What is the oxidation state of methane? -4, right? Which one makes a better fuel? Methane. So hydrocarbons are in a more reduced state, all right? And we can burn them, and they make good fuels. Hydrocarbons make better fuels than alcohol. We know that, okay? Alcohols make better fuels than carboxylic acids because the oxidation states, right? And so oxidation state comes into play a lot here. So you need to be able to calculate an oxidation state of a carbon atom on the upcoming exam. That would be fair game. Okay? Yes, ma'am.
Is a better representation of where the electrons actually are, then why wouldn't you push? I guess why wouldn't that be considered over just formal charge with mechanisms?
Oxidation state is important in terms of mechanism. Formal charge has its advantage in that it allows us to identify areas that have partial positives or real positive charges associated with them, and that allows us to understand something about how the electrons are moving. So when we're pushing arrows, right, you always want to push your arrows to a positive charge. a little more difficult to see that just by oxidation state. But it's a good question. Now, this is the easiest reaction mechanism I can possibly teach you. Okay? It's just like SN2 in a way. A carbonyl-containing molecule, like an aldehyde or a ketone, will react with a nucleophile. The nucleophile will attack the carbon of the carbonyl and break the weak pi bond. You end up with this alkoxide, which can then get protonated on workup with water to form an alcohol. Easy. Just a couple of arrows, right? The nucleophile attacks the carbon of the carbonyl because it's partially positive. It doesn't attack the oxygen. Yes, I can show arrows that don't break any rule going the other way, but it just doesn't happen because the oxygen has electrons around it, the nucleophile has electrons around it. They're not going to interact with one another. We go from what kind of geometry at this carbon? We go from a trigonal planar geometry to a what? To a tetrahedral. And you will hear organic chemists refer to this as a tetrahedral intermediate. You need to know when I say you get a tetrahedral intermediate, you need to know what I'm talking about. I'm talking about a carbon atom that went from an an sp2 hybridization to an sp3 hybridization, and now we have a tetrahedral carbon atom. We have just formed a carbon nucleophile bond, and quite frequently the nucleophile can be carbon, and so we can form carbon-carbon bonds this way very easily. The alkoxide can then go on and do a number of other things. I could take that alkoxide and I could react it with an alkyl halide and I could do a Williamson ether synthesis. You all did that in some of your problems on this last inverted lecture. The alkoxide was generated from ring opening of the epoxide, and then that was treated with something like iodomethane, right? But quite frequently in these reactions, we simply take the tetrahedral intermediate, or the alkoxide, and we dump it into water. And water will then protonate the alkoxide, and we will make an alcohol. So formally, this is an addition reaction across the carbon-oxygen double bond to make a new carbon nucleophile bond and a new oxygen-hydrogen bond. We're simply doing addition chemistry over 2 steps. Okay? So it's very similar in a lot of respects to all the addition chemistry you learned already. You're breaking a weak pi bond. You're adding 2 things across that pi bond. The mechanism is slightly different, however. Okay? This results from a nucleophilic attack on the pi bond as opposed to the pi bond being the nucleophile as we learned in previous chapters. Okay? And it has to do with the fact that that oxygen atom creates a dipolar environment where the carbon of the carbonyl wants electrons. Okay? Now, a couple of nucleophiles that you need to know. This is where reagents are starting to come into play. And again, you need to be able to memorize and understand your reagents. There are 2 reagents that are quite favorable in organic chemistry that have H- nucleophiles. Sodium borohydride, which we've talked about before, in what reaction? Not the hydroboration, that was borane. Not BH4, that was BH3. We used this in the oxy, and we used it in the demercuration step, right? It was a reducing agent. Sodium borohydride works really, really well for that. Lithium aluminum hydride is another reagent that functions as H-, okay? It turns out that if you look at the metals and the hydrogen, it turns out that hydrogen is more electronegative than most metals, and so hydrogen is pulling electrons to itself. It makes these reagents behave as if they are H-. Notice I have that in quotes. Why do I have that in quotes? You really can't have that floating around, okay, in this reagent. But it behaves as if it were H-. Okay? So, for example, if we take an aldehyde and we react it with sodium borohydride, we get an alcohol. Likewise, we can take this aldehyde, react it with lithium aluminum hydride, and also get an alcohol. We are formally adding H2 across the carbon-oxygen double bond to get an alcohol. but we're not using hydrogen gas and palladium catalyst. We're using sodium borohydride. Which of these two hydrogens comes from the sodium borohydride? The bottom one, the one to the carbon, because the sodium borohydride is the nucleophile, right? And the one that's on the oxygen comes from the water, right? And so we are adding hydrogen across the carbon-oxygen double bond. Now, there's a couple of things that you need to know about sodium borohydride and lithium aluminum hydride practically. I can right now make a solution of sodium borohydride in this classroom in water. I can take water, I have to make it a little bit basic, and I can put sodium borohydride in it, and I can make a solution. Nothing fancy will happen. You all look at me and go, well, that was exciting. I can do exactly the same thing with lithium aluminum hydride, but you'll get really excited because it will explode. As soon as lithium aluminum hydride comes into touch with water, it immediately reacts with that water and forms hydrogen gas at high temperature, which ignites. Okay? So lithium aluminum hydride, you cannot do the reaction in water or alcohol. But you can do the reaction of sodium borohydride in water or alcohol. You all are actually going to do this reaction in lab. I don't know when. You're going to reduce a ketone, and you're going to use sodium borohydride to do it. We are not going to allow you to use lithium aluminum hydride because we would have several fires around the lab that we'd have to put out, and hopefully it wouldn't be you. Okay? So why do we need two reagents if one is safe, relatively speaking, and one seems to be fairly hazardous? One is certainly cheaper. I can certainly buy borohydride a lot cheaper than I can buy lithium aluminum hydride. One will reduce additional things. So it depends on what you mean by better. There is some selectivity that we're going to learn about. Sodium borohydride typically only reduces aldehydes and ketones, whereas lithium aluminum hydride will reduce aldehydes, ketones, but also carboxylic acids and esters, whereas sodium borohydride does not reduce those other functional groups, and it has to do with the oxidation state. Okay? So I like to think of lithium aluminum hydride as strong hydride and sodium borohydride as mild hydride. Okay? The mechanisms by arrow pushing are exactly the same, but the chemistry in terms of selectivity can actually be quite different. Okay? So Anna comes into lab. She has 1 mole of aldehyde. She wants to reduce it to the alcohol. How many moles of sodium borohydride does she need? It is not 1 to 1. It's not 2. How many hydrides do I have on sodium borohydride? I have 4. I only need 1/4 as much. All 4 of those hydrogens are active. Okay? It can actually transfer all 4 hydrogens. And the mechanism gets a little more sketchy as you go along. A little more arrows that you have to push. But it's essentially the same thing. Okay? You can think of it as 4 equivalents of hydride. Okay? So, let's look at the mechanism on the board. There is the easy mechanism, and then there is the real mechanism. Which one you want to look at first? Everybody always wants to look at the easy one first. So let's take a ketone. Let's just take acetone. And we're going to react it with sodium borohydride. And let's do this reaction in water. And we're going to form isopropyl alcohol. The easy mechanism is to just think of sodium borohydride as H- and put it in quotes, because I know it doesn't really exist. Now what happens? Protonation of the oxygen, so we're in water, right? It's just an acid-base reaction. And I end up with the product plus hydroxide. Okay? Do you have a question? Oh, okay. So that's the easy mechanism. You just treat it as if it was H minus, and you do the arrow pushing. The real mechanism's a little more complicated. Okay? Let's think about the real mechanism. I don't actually have H minus floating around, do I? I just told you that. So what's happening? It does, but where do I start the arrow? Do I start with the B? Do I start with the H? Do I start with the sodium? What's that? I do have to move that. Let's redraw it just a little bit. And let's ignore the sodium for right now. The negative charge is on boron. So it's partially there because hydrogen's more electronegative than the boron, right? What about that bond between the boron and the hydrogen? Can it go to the hydrogen? It kind of can, and that would generate hydride, right? But we don't really have hydride. If that really happened first, we would have real hydride sitting in solution. Kind of happens at the same time. It goes from the bond to the carbon of the carbonyl, and the pi bond ends up reacting with the boron. And what you get is the hydrogen, plus you get an oxygen with B and 3 H's. This can continue to react in the same mechanism. And you can draw that again. You can draw that 3 more times, right? And then at the end, when it's all done and said, the water hydrolyzes the boron-oxygen bonds, and you end up making the alcohol and boronic acid. Okay? So this can continue over and over again. And then ultimately you end up with this species with 4 of these. That looks kind of hairy, right? And then the water hydrolyzes these bonds off, and you end up making the alcohol. Okay? That's really what's happening. And that's kind of complicated. I like this mechanism better. What's that, Anna? For sure? Okay. But I want you to understand what's really going on. Okay? Yes, it behaves as if it's hydride, but there's no hydride around. Okay? It has to do with the fact that this bond is actually polarized the way that it is. Having said all that, this is kind of the first layer of the onion you need to memorize. Aldehydes get reduced, regardless of the reducing agent, to primary alcohols. Ketones get reduced to secondary alcohols. Carboxylic acids get reduced to primary alcohols, and esters get reduced to primary alcohols and another alcohol, whatever this happens to be from the ester. So there will be, depending on what this ester is, if that's a secondary carbon, it'd be a secondary alcohol. But if you think about the reduction of the carbonyl portion, it's a primary alcohol. This is real easy for you to remember. Everything gets reduced to a primary alcohol with the exception of ketones. And ketones get reduced to secondary alcohols. That's easy to remember, right? Now notice I have put H in bracket. meaning that we don't really think too much about the reducing agent. It doesn't really matter what the reducing agent is. Okay? However, reducing agents, as we mentioned before, lithium aluminum hydride is more reactive than sodium borohydride, and so we do see some selectivity in terms of those reagents. So let's look at some examples. So if Jack comes in and he needs to reduce propanal to a primary alcohol, he can simply take propanal, which is an aldehyde, sodium borohydride, and water, and he's going to get 1 propanol. The reaction's over really quick, good yield. Okay? If Bailey comes in and has cyclopentanone, that's a ketone. He knows that's going to get reduced to what kind of alcohol? A secondary alcohol, cyclopentanol. However, if Anna comes in with this keto ester, meaning that we have a functional group that's a ketone and we have a separate functional group in the molecule that is an ester, and she reacts this with sodium borohydride, only one of those functional groups gets reduced. Which one is it? Yes, the ketone, right? The ketone gets reduced, but the ester does not. Sodium borohydride is selective for the reduction of aldehydes and ketones. It typically leaves esters and carboxylic acids alone. Can I get sodium borohydride to reduce an ester? Yes, we do it all the time in my lab, but you have to add additives for that to happen. You have to convert sodium borohydride into something else before it can happen. Okay? But for the purposes of this class, sodium borohydride does not reduce esters and carboxylic acids. So, if Anna wants to reduce the ketone in the presence of the ester, she's fine and dandy. She can pick sodium borohydride and selectively reduce the ketone. No problem. However, if we change the reagent to lithium aluminum hydride, by the way, lithium aluminum hydride, you can do LiAlH4, or you can just write LAH. 3-letter abbreviations are good, right? So you can do LAH. Notice the difference. In all of these cases, you have step 1 and then step 2. Did we have that in the previous example? Nope. This means that sodium borohydride is in solution with water while this reaction is occurring. What does this mean? It is separate. So here we have lithium aluminum hydride and ether, which is dry, no water around. We add the ketone. We allow that ketone to react until it stops reacting. Then we dump it into water. If we mix lithium aluminum hydride and water together, we have an explosion. We do not have a reaction that's productive. Okay? On your inverted lectures and on the exam, if you write LAH/water, that is wrong. You have to explicitly show the steps. Okay? But we get a secondary alcohol. We get a primary alcohol. The reduction of this carbonyl gives me my primary alcohol plus methanol, which comes from this part. We'll talk about that in the mechanism in the reduction of esters later. But notice what happens in the reduction of the keto ester. This gets reduced, and this gets reduced. And of course, we will have the methanol as a byproduct as well. Okay? Why do you suppose that sodium borohydride can't reduce an ester? Okay, that may be a good argument, steric crowding. I would argue that methyl group's not very big, though, on a methyl ester. Isn't a ester more oxidized than a ketone? So why would sodium borohydride not reduce something that's more oxidized? It is weaker, but it seems to me that if something is weaker, it would react with something that's stronger or more oxidized. Doesn't have enough strength. You're on the right track. Think about the resonance structures between a ketone, between a ketone and an ester. That'll give you some insight. So think about that for next time. Okay? What's time we got? let's think about the mechanism real quick in the reduction of an ester. So let's just take a simple ester and let's reduce this with lithium aluminum hydride followed by water. What's my first step going to be? We're in step 1, right? How am I going to think about this? How do I think of lithium aluminum hydride? Think about it as H minus. So my H minus attacks what? And does what? Breaks the pi bond. I end up adding my hydrogen, and I end up getting my tetrahedral intermediate. But is that the end of it? Okay, if water comes in, do I get the alcohol that's the product? I would end up with an alcohol here and an ether. It's called a hemiacetal. It's a functional group we'll learn about later. But that's not what we get, right? We get a primary alcohol plus this alcohol too, right? We got to cleave this bond somehow. How does that happen? This tetrahedral intermediate collapses. This is an alkoxide, right? This can come back as a nucleophile and kick out another alkoxide. pKa's dictate that that can happen. So I end up with an aldehyde plus methoxide. What happens to an aldehyde in the presence of lithium aluminum hydride? It gets reduced, right? And so it will get reduced again. So we will pick up with that. So think about that mechanism for Friday. Your inverted lecture is due today, so on your way out, just put it up here at the front. I will get everything posted to YouTube a little later. The Chapter 12 homework is already available on Sapling, so please go ahead and get started on that.